Okay, so I would first like to thank Fran for the kind invitation. It's really a pleasure to speak at Rockwell University of Science and Technology. So today I'm going to talk about an effective action for superconductor near the critical point. This is based on a recent work with Yan Bu at Harbin Institute of Technology and my colleague Mitsutoshi Fujita at Sun Yat-Sen University. We have also I will also briefly talk about an ongoing work with the same people. So let's now start with some motivations. So it is according to Abrikosov's theory of type 2 superconductor. The phase diagram schematically looks like this. So it can be divided into 3 regions. So there are, as a function of temperature, there are 2 critical value of magnetic field. So below the lower critical magnetic field, the superconductor expel the magnetic field entirely. So this is the Meissner state. And if the magnetic field exceeds above this critical line, then the superconductor enters the intermediate state. So magnetic field, external magnetic field can penetrate into the superconductor in the form of vortices. And in this state, the superconductor can only induce the magnetic field by the superconductor can only partially cancel the external magnetic field. When the external magnetic field is even larger, exceeding the second critical magnetic field, then the superconductor will be destroyed entirely. This is according to the traditional Abrikosov theories. And it is known already back in the early 90s that in this review paper, it is mentioned the actual phase diagram for superconductor as a function of magnetic field and the temperature looks as follows. It is pointed out that the thermal fluctuations and disorders in the superconductor can play a very important role in modifying the phase diagram. In particular, you will find that in the intermediate state will be changed when thermal fluctuation and disorder are taken into account. So this intermediate state will be further split into 2 parts, the vortex glass and the vortex liquid. So what I'm going to focus on the effect of thermal fluctuations. By the way, so if you have any questions, please feel free to interrupt. So the question is, how do we include thermal fluctuations? Of course, the inclusion of thermal fluctuation dates back even earlier. So already in this review paper by Hohenberg and Halperin, it's known that the inclusion of thermal fluctuation is simply to add a noise term in the evolution equation of the condensate. And here the F is the free energy, so which can be near the critical point. It can be expanded up to quartic terms like this. This is a gradient term, and the mass term, the mass can be positive or negative depending on which side of the phase the state is. And this is a quartic term. And the noise is usually taken phenomenologically as a Gaussian white noise, taken to be this form. Sorry, there should be a bracket here. And the magnitude of the noise is characterized by a parameter gamma. And the same gamma appears in the force term. So this is a force term, and this is a random force term. So the appearance of the same gamma guaranteeing that the fluctuation-dissipation theorem is satisfied. So this is the early ways of introduce thermal fluctuations. And we can actually, there's a there's an equivalent form of the Langevin equations. It can be converted to a Fokker-Planck equations, which is formulated in terms of this variable. This variable is the probability of finding the condensate at value delta at time t. So this probability function satisfies a Fokker-Planck equation, which is equivalent to the Langevin. Here, for simplicity, I set temperature to 1 and turn off the spatial inhomogeneity. If we look at these equations, so obviously this term comes from the fourth term, the gradient, the derivative on the free energy, and this term comes from the thermal fluctuation, the noise term, and we can see that.
Let me interrupt you
yes?
one second. So temperature is 1 in units of delta, or
temperature. Well, temperature sets a unit. I use temperature to set the unit.
yeah, but in units of the condensate or what?
Then I take you may say that every field is divided by the temperature.
Okay.
So everything here, like you may say, if I take temperature to be 1, so I can convert back by say replace the T by T times temperature.
Okay.
And the condensate will be rescaled accordingly.
Okay. Good. Thanks.
And this the last term is of diffusive type. So right, this is partial T and partial X squared. So this gives a diffusion term. So this diffusion obviously is due to the noise. And we can easily look for the equilibrium distribution of the Fokker-Planck equation. So simply set the left-hand side to 0. So we found the following equilibrium distribution function. It's of Boltzmann type. And importantly, the magnitude of the noise, gamma, does not enter the distribution function. So this is a feature of the Gaussian noise, actually, as we will see later. So another way of reformulating the Langevin equation is to convert it to an effective Lagrangian. So this was done by a trick invented by Martin-Siggia-Rose in the 73. So the way to proceed is actually very simple. So we can put this equation motion onto the exponent by introducing an auxiliary field, delta hat. So integrating out the delta hat, we get back the equation motions. And also we know that we have Gaussian noise, Xi. So we can actually also this is a noise with Gaussian weight. Since here we see that the noise is only linear in the exponent, so we can actually integrate out the noise and to arrive at the following form. So the partition function becomes exponent of this form. So we may identify this as an effective action involving with the field being delta and the delta hat. So here there are two crucial points. One point is that the Gaussian noise here, the Gaussian noise allows us to fully integrate out the random field Xi. So this is a special feature of Gaussian noise. So we can do Gaussian integrations. And also, if we look at the effective action in the green box, so we see that this part is Hermitian, but the last term is not. So the non-hermiticity actually, obviously, it comes from the noise, because the noise will introduce fluctuations. The evolution becomes non-unitary. So it is reflected in the non-hermiticity of the effective action. So this auxiliary field delta hat is not just auxiliary. So in a slightly modern field theory language, it can be delta and delta hat can be mapped to the fields on the Schwinger-Keldysh contour. So this is a Schwinger-Keldysh contour. So we have insertion of delta 1 and delta 2 on the upper and the lower branches. And out of this delta 1 and delta 2, we can construct their mean and their difference. Their difference actually correspond to fluctuations. So delta and delta hat in the previous page can be mapped to the two fields. So we see that after this mapping, the delta hat is not just auxiliary, but becomes fluctuations. So we can write down the effective action before in terms of just by a change of variables. So the effective action becomes of the following form. So now comes the questions. So we know that previously I emphasized the noise was introduced by hand as phenomenologically as a Gaussian noise. But now if we are given this effective action, so the question is this really complete actions up to quartic order? So these are just the quadratic terms. So the quartic term is only this one. It contains only one delta A and delta R cubed. So in principle, we could have other types of quartic terms like this one, and also these kinds. So this one actually is still, you see that it is still quadratic in delta A. So essentially it is Gaussian, except that it modifies the coefficient of this term. So this kind of terms are extensively studied in the literature. So this is nothing but making the Gaussian noise multiplicative. So with this kind of weight. But these two terms are actually non-Gaussian. So this is not really well studied until very recently. So we will mainly focus on these non-Gaussian terms. So with this preparations, let me discuss two aspects of non-Gaussian Gaussian terms. So first of all, whether they exist. So their existence actually have been demonstrated in explicit models, such as in these works by Indian groups. So they studied the QXY model and holographic heavy quark models. They found that indeed the non-Gaussian terms exist. They are not necessarily suppressed by some parameters. And on the other hand, so there are also phenomenological studies of non-Gaussian terms. So one particular directions I want to mention is the hydroeffective field series. So what this is, this direction is actually pursued actively by many groups around the globe. So what they do is they write down an effective action for hydro, and then consider fluctuations. I'm taking, for example, let me explain with this, explain the result of this papers. So what they did is they consider a diffusion, which is the slowest mode in hydrodynamics, as their basic degree of freedoms, and they write down the effective action for diffusion mode, and then the diffusion mode in a medium, the diffusion mode can be generated by fluctuations, and the fluctuations can back react, and it can appear in hydro loops. So by doing loop calculations, they found the correlator, the retarded correlator of density operators changes from this one to this one. So this one is easy to understand. This is nothing but the prediction by the non-fluctuating hydro theories. So it contains a diffusion pole here. And what they found is when they take into account loops, the loops which contains fluctuating diffusion waves, the retarded correlators takes the following forms. So the denominator gets correction from the self energy, and also the conductivity gets corrected. Very interestingly, the analytic structure of the retarded correlator changes entirely. So instead of a simple pole, it develops a branch cut extending from infinity to halfway of the diffusion pole. And there are also two separated simple poles. So the phenomenological consequence of introducing the fluctuation could be very complicated. So with this somewhat long motivations, let me so let me introduce what I'm actually going to talk about. So I will first talk about the first part of my talk will be non-Gaussian corrections to superconductor effective actions. So I will first introduce the non-weak coupling result. And then I will introduce the strongly coupled method I use and the result. It turns out these two, the weak coupling model and the strongly coupled model, are quite comparable. So it turns out they are in the same the universality class, and we will compare the result, and we will find that in the strongly coupled method, we obtain many non-Gaussian terms which are absent in the weak coupling method. So this is basically a proof of their existence from the holographic model, from the strongly coupled models. And the second part will be phenomenological studies. So we will study the consequence of non-Gaussian corrections. So we will write down an effective action and explore what is their phenomenological implications. In particular, I will briefly mention that it modifies the Fokker-Planck equations. So okay, let me start with the weak coupling result. So it is known that so the effective action for a superconductor can be split into three parts. So the first part is the Ginzburg-Landau effective action for the condensate, denoted by the delta here. And the second part is a coupling between gauge field A and the supercurrent. To see this is this imaginary part is the supercurrent. We can see this is a gradient acting on the condensate, and times the condensate the star. So this is proportional to the phase velocity of the superfluid component. So this indeed corresponds to the coupling between gauge field and supercurrent. And the last part is the coupling between gauge field and normal current. So it is also easy to see why this is a normal current. So the partial T acting on the gauge field is the electric field. And this prefactor nu times D is nothing but the conductivity. So this sigma conductivity times electric field is the normal current. So this effective action corresponds to the coupling between gauge field and normal current. So we will identify, so they have, this form of effective action use a slightly different notation. So here this delta classical means in our language it's the mean value, and delta Q quantum means the fluctuation difference, delta A, and similarly for the gauge field. Let me, since I will compare the critical exponent, let me briefly, I think this is well known, but let me just for completeness quickly go through this. So a phase transition is characterized by a set of critical exponents. So the first set is static ones. This is determined from the scaling laws. And this epsilon t is a measure of the deviation from the critical point. And there's, apart from the static critical exponent, there's also a dynamical one. This dynamical ones is relates the relaxation time of the order of the condensate, the order parameter, with the correlation length of the system. So it is given by the following scaling laws with a new dynamical critical exponent z. So these exponents are known in the weakly coupled superconductors without fluctuations. Without fluctuations, the static critical exponent is just of mean field type. And the dynamical ones, it is found to be belong to the model A in the classification of Hornberg and Halperings. So this dynamical critical exponent z in model A is related to one static exponent eta in the following way. So let me further analyze the slow modes in the superconductor. So at very low frequencies, the slow mode are charge diffusions, which is given by this dispersion relations. And the other one is a relaxation of the order parameter, the condensate, which is given by this dispersion relations. It's actually just from the inversion of this scaling law. So very close to the critical point, the correlation length diverges. So this omega approaches 0. So comparing these two modes, both are slow mode. So suppose we are very close to the critical point, and if we want to have the two modes to be comparable, we will have to have very small q, very small momenta. So this actually so for very small momenta, the fluctuation is suppressed because q is small, so the phase space is small. So by going very close to the critical point, we may just focus on the dynamics of delta and ignore charge fluctuations. So with this reasoning, we will aim at the Ginzburg-Landau effective actions, meaning that we will just study the first part and leave these for the future. And so far, any questions? So if not, let me continue. So these are general discussions and about what we will aim at. And now let me introduce the method. So the method I'm going to use for strongly coupled superconductor is the so-called gauge gravity duality. So according to Maldacena, so there's an duality between weakly coupled gravity and the strongly coupled field theory. So this is very nicely illustrated in this figure. So the background is a 5-dimensional anti-de Sitter space-time, and there's a black hole in the center. So this 5-dimensional gravity background is dual to can be mapped to 4-dimensional field theory on the boundaries, and in this case, the field theory is a finite temperature field. So this is the basic idea of the dualities. So by studying the behavior of fields in the 5-dimensional background, we can get information about such as correlation functions in the finite temperature system. So to be a little more specific, so the background we will use is the following. So the ADS Schwarzschild background, written in Eddington Finkelstein coordinate. So this V will be our time. There's a special role of the radial coordinate. It runs from the horizon to infinity. And at the boundary of the black hole, we have fields at finite temperature. So we need a model for a superconductor. So the corresponding model was constructed by Gupser and Hartnell, Herzog, and Horowitz. So the idea is the following. So by introduce Maxwell field and complex scalar into the background, we can have the following phase transitions. So when the temperature is high, the background is simply the complex scalar vanishes. The background is simply ADS Reissner-Nordstrom. But below a certain critical temperatures, the background becomes unstable. It starts to develop scalar hair, complex scalar hair. So it becomes a hairy black hole. So the development of complex scalar is due to because psi, the complex scalar, is due to the condensate. So it corresponds to the formation of condensate in the superconductor. So this is the holographic superconductor models. So it turns out in the holographic superconductor models, the critical exponents for static ones and the dynamic ones were both studied for S wave by this Japanese group, and for P wave by us. And it turns out the static critical exponent is also of mean field type, and the dynamical exponent is equals 1. This also belongs to model A in Hohenberg-Hypering's classifications. This means this gives us, so recall that in weakly coupled superconductor, the critical exponent are also of this type. So this provides a ground so that we can make close comparison between the two models. So how do we actually get the Ginzburg-Landau effective actions? So according to the gauge gravity duality, we simply relate the 4-dimensional effective action to the 5-dimensional on-shell action of the on-shell action of this 5-dimensional action. So we will do the following. So we will take the temperature take the temperature to approach the critical one from above, and then we take the condensate, since we are interested in the state slightly off equilibrium. So we will take the condensate to be slow varying on the boundaries. So in particular, we take the variation along the time directions and take it to be very small, much smaller than the typical scale, the temperature of the system. And for simplicity, we turn off the spatial inhomogeneity. And also the gauge field vanishes on the boundaries. So taking the variation gradient to be temporal gradient to be small, this is actually very similar to the fluid gravity approaches. So along the line, actually, Pietro and Fran have contributed a lot in these directions. So we basically follow this method. So there's one important question. So we know that in the fluctuating case, the effective Ginzburg-Landau action is non-Hermitian, as I mentioned earlier. So the question is, how can we recover this non-hermiticity from the gravity on-shell actions? The answer is easy for an equilibrium black hole. So we know already back in 2002 that the retarded correlators can be studied by imposing an ingoing boundary condition for fields on the horizon. So this is natural because black hole horizon absorb everything. So this introduces non-hermiticity to the actions, and also the retarded correlator, we know that it encodes dissipations. So this is not enough. We still need fluctuations. And to have fluctuations, we need all the real-time correlators, in particular the symmetrized correlators. And it is known that it is established by Song and Herzog that in order to have the 4 real-time correlators, what they did is they put the scalar field in an eternal black hole. So the eternal black hole has 2 boundaries. It naturally corresponds to delta 1, delta 1 and delta 2 in the Schwinger-Keldysh contour. So by demanding analytic continuation along the on the horizon, they found that actually both ingoing and outgoing modes have to be present. And the mixture of ingoing and outgoing modes allows for both dissipation and fluctuations. So this naturally incorporate the 2 effects in equilibrium case. And generalizing to off-equilibrium case, so this was done in 2008 by Skandaris and Van Ries. So what they did is basically they extended the Schwinger-Keldysh contour into the bulk. So there are 3 branches, so they have 3 patches, and the 3 patches need to be glued in the bulk. So this is possible, but technically complicated. And more recently, Glorioso and Liu introduced a more convenient method. So what they did is instead of complexifying time, like in Schwinger-Keldysh, what they propose is they extend the radial coordinate in the complex plane. So this is a complex plane of the radial coordinate. What they did is they introduced such a contour, make it wrap around the horizon, r equals RH. So now, we see that there are also 2 boundaries, two boundaries, and the 2 boundaries naturally can have 2 insertions, delta 1 and delta 2. So this is a method we use. And we use the following perturbation schemes. So we have the temperature slightly above the critical temperature, so that we can do the expansion in delta mu. Delta mu is a measure of the deviation from criticality. So we will truncate up to 1st order in delta mu. And also we have a slow varying condensate. So we will truncate to the 1st order in the time derivative. Here V is our time.
Yes. Can I ask you something? Can you go back to the previous slide?
Mm-hmm.
I mean, in the case of like a Schwinger-Keldysh, I kind of like, okay, I have like the intuition why you have to integrate on that contour, and why you have like this imaginary time, because you have, I mean, to describe equilibrium, you have to have your field theory in the Euclidean, signature, and temperature is basically the thermal circle, basically the radius of like of your Euclidean time. But then in this prescription, what you're saying that you are complexifying this radial coordinate, what is like the role of this epsilon? And I mean, can you just like give some intuition on the field theory perspective? What are you doing?
0.
I mean, but from the field theory perspective,
like this somewhat. I mean, this in Schwinger-Keldysh, I mean, the 2 branches can be very close to each other when you take the sigma to be 0. Right. Well, I mean, this is kind of similar in this radial contour. So the 2 branches are also very close to each other, and this is an infinitesimal circle around the horizon. Well, apart from that, I don't have more intuitions why this works, but it turns out it works very well. In particular, in hydro, in effective field theory for diffusions, it is demonstrated by them that it gives the correct effective action.
Okay, thank you.
Yeah, thanks for the question. And apart from these 2 small variables, delta mu and delta and partial v, and we also have one more expansion. So we assume the fluctuation of condensate or the parameter being small, so that we keep only the quadratic and the quartic terms. So with these specifications, let me jump to the results. So here's our result. So the first term is the first piece is a quadratic action in the condensate, actually in the fluctuations, and the second one is proportional to the deviation from criticality, and the third one is proportional to the variation in time, in gradient in time. And the last one is an important one, which contains all the quatic terms. So let us now compare these results with the weak coupling result, weak coupling counterpart. So here's the structure of the weakly coupled result. So it is mostly written as a quadratic terms. Except that these correlators contain propagators contains a quadratic term in the condensate. So this gives when you plug in this into L inverse R and L inverse A, this gives quatic terms. So this is only quatic terms. And let us first compare the leading order term. The leading order term comes from this one. So this one is proportional to, is given by this number. And in our case, it's very similar. So it's also quadratic in the delta A and purely imaginary. And the overall constant is different, which is not too surprising because we are comparing two different models. But the structure are exactly the same. Let us look further. So the next term will be proportional to the delta mu. So in the weak coupling case, it comes from this term. So the tau is a inverse. The tau is a relaxation time, and which is proportional to, it diverges as one approaches the critical point. It diverges this way, and this term, the orange term, corresponds to, in our case, this orange term. So also proportional to delta mu. And in fact, this exponent -1 is entirely dictated by the critical exponent, because as I mentioned, the weak coupling model and the strongly coupled model are in the same universality class. And so we can determine from their critical exponent, we can determine the scaling, so which is exactly -1. So apart from these agreement, we do have one particular corrections, and these corrections actually can be combined, should be combined with this term. So which means the deviation from criticality gives a correction to the fluctuations characterized by the quadratic terms in delta A. So also we have terms proportional to the time derivative. So in weak coupling case, it comes from this term, and in our case, it comes from it contains many terms. So we can actually identify this term with in our case, these terms. And the difference is, instead of having real coefficient, we do have complex coefficient. And we also have these red terms, which are absent in the weak coupling case. And by the way, I should have mentioned that the coefficient of this term is not independent. It's actually clearly from this expression that it is constrained by the KMS relation, which relates the retarded propagator to the symmetrized propagator. So in our case, one may worry about the KMS relations. It turns out only the real part enter the KMS relation. So and also this term is proportional to frequencies. So in fact, it only constrains the retarded correlator at higher order in frequencies. So basically, these corrections leave the KMS relation intact. So finally, let me come to the most important difference. And as I mentioned that the effective action, the quadratic term in the weakly coupled case only has this one. So this is of the type delta A and delta R cubed. So recall that this delta classical is just delta R. So we have delta A and delta R cubed. But in our case, we have all possibilities. So these orange terms correspond to their case, this delta A and delta R cubed. And we also have delta A to the fourth, delta A cubed, and etc. So basically, we have all other non-Gaussian terms. They are allowed. And indeed, we found that. So this basically finished the first part of my talk. So we found we confirmed that in a strongly coupled holographic superconductors, we have all possible non-Gaussian terms. For part two, let me explore the effect of fluctuations.
Shu, before you start like the next part, so you have like 5 minutes, so maybe you evaluate.
The next part has only 1 page.
Okay.
But I mean, if there's any questions, please feel free to ask.
Yeah, actually, I have some questions, so I got lost a bit.
Yes, please.
In the course of your talk. So usually, like in the Landau-Ginzburg action, you have like fermionic fields, and then you introduce this Hubbard-Stratanovich transformation, then you get deltas. So what happened to fermions? You like integrated them out, or it's something else that you're doing?
Right. The fermions can be so here in the end the Ginzburg-Landau effective action is only contains the slowest mode. In here I try to argue at the beginning that the slowest mode is only the condensate, and the fermions is actually can be identified as fast mode. So they are. I mean, if you take the usual approach, so you write down the action and integrate out fermions. So this is a usual approach. And the fast mode, when the fast mode is gone, you are left with the effective action for the slow mode, which is a condensate. And here we are taking a slightly different approach. So we in holography, so this is the condensate is the only thing we can get in fact. So the condensate here this is our holographic actions. So the condensate comes from the boundary value of this complex scalar. So this is this method guaranteeing that we will end up with the effective action of delta only. So I don't know whether that answers your question or not.
Yeah, I guess to some extent, yeah. So another question I have is, is there any experimental relevance of this higher order non-Gaussian terms, or it's just like theoretical, let's say, endeavor?
Yeah, so very good. So in order to have to discuss experimental implications of these non-Gaussian terms, we first need to have some phenomenological predictions, right? So here up to now, what we have done is we construct this, we calculated this effective action, the 4 effective actions, and in fact, the action, although it contains the fluctuation, but it doesn't have included the fluctuation as a back reaction to the system. So in order to see the effect of these fluctuations, we need to take this effective action as a field theory and do the loop. So this will give some predictions for the effect of these non-Gaussian terms. So this is actually part 2 of my talk.
Okay, but so maybe another like related question, because you started with a weak coupling, and then somehow then you jump to like gauge gravity duality. So is it at the same footing, this like no Gaussian terms, or I mean, is it relevant both for like weak coupling and strong coupling, or I mean, do you have some classes of materials in mind, or is that completely separate?
Well, these are two completely different approach, right? The weak coupling is based on weakly perturbation theories, and this strong coupling is a holographic model. So, I mean, the fact that they are comparable already tells something, right? So they both have predictive powers, and what is different in our strongly coupled model is we do see the non-Gaussian terms, and it remains to see their effect in phenomenology.
So basically, the message is that it has not been included in like the weakly coupled models, and then you just include it in holography, and you see that there is some correction.
Yes, yes. So in principle, they are allowed, and I mean the fact that I mean the weak coupling method doesn't find it. Maybe it's I don't know. It maybe something particular to the weakly coupled method. That's not clear. But those terms we found those terms with our approach. So this justifies the I mean, this is the existence part, as I try to emphasize on in the motivation part, and then it comes to the phenomenological consequences of them.
But why is the existence like questionable? If you like in the effective field theory, whatever you add, then
let me jump in 1 second in the discussion. Since Shu has only one slide, like to finish the talk, maybe it's better just to let.
That's fine. That's fine. I think it's good.
We can just like come back to the questions of discussion.
Yeah, it's fine with me. But please go ahead.
I mean, yeah, you can finish and we can discuss afterwards if it's just
okay. Yeah, it's only 1 page. So okay. So let me discuss a little bit briefly the effect of fluctuations. So we write down the we simplified it a little bit. So we write down an effective action for real scalars just to see its effect. So the effective action takes the following form. So it contains 2 quadratic terms in the condensate, and other all possible quartic terms. So these in the absence of this epsilon 1, 2, and 3, in the absence of these terms, the action is well studied. So what we will do is we will, since it's aquatic actions, we can only do perturbations in these treat this epsilon as small couplings. So what we found is by following standard approach to derive Fokker-Planck equations, we found that the Fokker-Planck equations gets changed by the presence of these quartic terms. So in particular, we have, the most significant change to the Fokker-Planck equation is that it changes the leading derivative becomes a fourth derivative. And this is proportional to the epsilon 1 here. So instead of a simple diffusion, it becomes subdiffusions. So we can also solve the equilibrium distributions. It is certainly modified by these parameters. So it can be to the 0th order. It's the usual the Boltzmann distributions. So this is a free energy basically. And when we take into account these corrections from these epsilon, the corrections can be organized into the following form. So we may imagine that we re-exponentiate, put it on back to the exponent. So these would introduce non-Gaussian. These non-Gaussian corrections will actually modify the free energies. So I want to emphasize that in the beginnings, I said that the Gaussian noise actually doesn't change free energy. It only appears as it doesn't enter the free energy, but it seems to be violated by these non-Gaussian noises. So that's the one of the phenomenological implications. So with that, let me wrap up. So we have derived Ginzburg-Landau effective actions for holographic superconductors. And we found, in fact, the result of the strongly coupled model and the weakly coupled model are quite comparable. So the one reason is they belong to the same dynamical universality class. And apart from that, we found very interestingly, the strongly coupled model contains more complete quartic terms. And as further directions, it would be interesting to study the effective actions for coupling between the gauge field and the supercurrent and normal current. And also, since we already in the previous page, we already studied the modified Fokker-Planck equations. It would be also very interesting to study how the Langevin equations are modified by these non-Gaussian corrections. And furthermore, as an effective field series, it would be interesting to study the renormalization of parameters, so that how the renormalization of parameters can make the prediction finite. So with that, I will thank you for your attention.
Okay, thanks a lot for your very nice talk. So now it's time for questions. I guess Piotr has like more questions. So maybe Piotr, you can continue or.
My last question was why the existence of this higher order terms is like non-trivial if you, let's say, use this field theory picture that you add like term by term. So then in principle, all higher order terms are allowed. It's just they're like not as relevant probably, but maybe.
Yeah, I would take that point of view, right? But it seems that it's over a long time, people have ignored the non-Gaussian corrections. So that's why I try to emphasize their existence is it should be emphasized.
Okay, thank you.
So, but I mean, it's just like related with that question. So in principle, if from the effective field theory perspective, if they are allowed, so a priori they should be there. And if so far they, so let me see how to formulate the question. So I mean, the point is that, I mean, like, Ginzburg-Landau model is like a successful model, okay, and they don't include those terms. And with successful, I mean, it's just like, okay, then you compare whatever prediction from the model with experiments, and then there is like a very good agreement. And then is where it comes like my question, which is somehow related with Piotr's question. It's like now, okay, these terms in principle are allowed by symmetry, but people have like overcome them. But somehow it seems that experiments don't care about them. So what's just like your view is just like maybe you should have like some more exotic kind of like a superconductor state, or what's your view?
Yeah, somehow I think we need some observables which are very sensitive to the to the fluctuations. So yeah, I don't know. I'm not an expert on the superconductor, so I don't know whether there are such. I mean, one thing I know is the phase diagram can be changed significantly. So apart from that, well, I don't know if some correlation functions of, say, condensate can be sensitive to the non-Gaussian terms.
So I mean, like maybe rephrasing the question, how much do you think is like relevant the strongly coupled nature of your microscopic theory on the presence of those non-Gaussian terms. Because
I
somehow you're
don't
saying
think-
that you are just like your low energy theory is still like in the same universality class of somehow you don't care if your microscopics is just like a strongly coupled or weakly coupled, because in the end, in the IR, you are running to the same class of theories. And then my question is, how important is the strongly coupled nature of your microscopic system in order to generate them? So how, maybe that's, I don't know if that's the right question or.
Yeah. I understand your question. I think the fact that the strongly coupled and the weakly coupled models give the same correspond to the same universality class. I think there are the separated reasons. I think I mean in holography we are. I mean we may imagine, although it's a bottom-up model, so we may imagine this is from some large n limit. So in the large n series, the things tends to becomes acts like mean field. So I think this is a reason for the strongly coupled model to be in the same universality class. Somehow so that the two models are comparable, but whether these non-Gaussian terms are yeah, I think it's not say unique to strongly coupled models, and somehow in weakly coupled method it has been ignored so far.
Okay, thanks. Any other question from?
Okay, may I ask a question?
Yes, please.
I admit I understood rather little from your talk, but I have a very general question, because you're talking about fluctuations, and the fluctuations are strong close to the phase transition, and you assume in the beginning temperature equal as the unit, T equal 1. How can you be sure that you are close to the critical point? What's the controlling parameter which decides that you are close to the critical point?
I think setting temperature to 1 is only sets a unit. I think we can always do that.
Yeah, but you have to be close to TC in whatever unit you'll decide to use.
Okay, I'm sorry for the confusion. So here it means like I think okay. It means I take TC to be 1.
Okay.
Sorry for the confusion.
Okay, then
it shouldn't be the temperature shouldn't be a variable.
Okay, then my next question, maybe we can get a little bit closer to the Earth. Concerning some experimental results, can you draw some real physical conclusions from this form of action? For example, when you approach TC from above, there are fluctuations in there are changes in conductivity. For example, the famous Mackie-Thomson contribution, which cannot be derived from the regular Ginzburg-Landau action. Can you obtain this effects from your action?
Currently not, but this is certainly a possible thing to do. So because currently we only have the Ginzburg-Landau part of the effective actions. So in order to have correction to conductivity, we need to include also the other two parts, the coupling to, in particular, coupling to the normal current. But this is certainly doable.
Okay, thank you.
Thank you.
So if anybody else has a question, please unmute yourself. So if not, so we can thank Shu again for the very nice talk. So I will just stop recording, and then we move to the informal part of the seminar.